Búsqueda de nueva física en aceleradores del cosmos. Today we have the president of Zihanzhou. I don't know if it's correct, the pronunciation. And Jonathan is going to make a presentation about you. Jacobo.
Yes. Okay. Hello, Zihan.
Hello, hello.
Are you ready to?
Yeah, I'm almost ready. Just a second. I need to prepare the chargers for my computer.
Okay.
Put
So
down.
in the meantime, I think I can introduce you to the group, if you don't mind.
Okay.
Okay. So first part, I guess it will be in Spanish. Or no, it's fine. Okay. So welcome to this week edition of the seminar of our working group in searches for new physics and the cosmos. Today we have Zihanzhou in China. He did his undergraduate studies at the University of Science and Technology of China. And he's currently doing his PhD at the University of Princeton, where he's currently working mainly on theoretical aspects of gravitational waves, amplitudes, and effective field theories. So thank you very much, Zihan, for taking the time to give us a talk. And yes, you may start now. Thank you.
Okay. So thanks for the kind invitation. I'm very happy to be online and to give you this type of talk. And today I want to share some interesting work I've been doing. It's about how we connect black hole perturbation theory and with scattering amplitudes and even with conformal field series. So the talk will be when black hole perturbation theory meets amplitudes and CFDs. So the talk will be based on the following 4 papers, and all of them are now published online, so you can all just go and check it. Okay, so let's just jump into the talk. So we all know that this decade is a very good time to study black hole physics. So now it's as you know, so like now we have over 200 events in total for the like over collaboration. We have already seen many black holes, one neutron star merger, and several neutron star black hole mergers. And at this stage, I would like to tell you that we are at the end of the O4 observing round. So the O4B, the second stage of the O4 observing round, has ended in this year June. So now we have many more data. Also, I think in August, the collaboration published the first stage of the O4 round, so we can already analyze the new data from the merging of the binary systems, binary black holes mainly. Okay, but now we have a lot of more events, so this also motivates us to come up with accurate and a very faithful description of the binary systems. So we need a lot of theoretical tools to help us understand the binary black hole dynamics. So now I think in the community, we have 3 main tools to understand the binary dynamics. The first tool is called post-Newtonian effective field series. So which by the name, you can already know that it makes a post-Newtonian expansion, which is this V over C expansion. Assume the speed of the binary system is much smaller than the speed of light. Another expansion is called the weak field expansion. It uses the modern techniques of scattering amplitudes. It assumes that the expansion of G, which is the Newton's constant, is small. It's a weak field expansion. While another way to understand it is they have a binary system, a binary black hole. They're separate apart. So because of the large separation, so they're in a weak field limit. This is the small G expansion. And there's another expansion which typically people also use. It's called mass ratio expansion, named self-force. So basically, you assume for the binary system, the second guy is much smaller than the first guy. The mass is much smaller, and you can do an expansion in terms of mass ratio. So it's also another regime we can study the binary dynamics. And all of these regimes, they are not just independent. They have a lot of overlap regimes, which allows us to test the consistency of the results and allows us to understand the mathematical structures of the result. So this is a very interesting like intersections that I will talk about today. So I will talk about how we can use both of these three techniques to play the piano trio of the black hole dynamics. So how to do that is we also need to understand what is missing at the current stage, because Einstein has established his general relativity hundreds of years ago. So a lot of techniques has been established, a lot of things has been understood, but what is still missing, and we need to understand use the modern techniques. The first thing that is still missing is we don't quite understand the internal structures of compact objects. For example, the leading order effects come from the internal structure of the compact object. It's called tidal deformations. So most of the current waveforms nowadays include the static tidal deformations of the, let's say, the neutron stars, which is large, and for black holes it's small, it's zero. But nowadays, I think people don't quite understand the dynamical properties of these tides. So the dynamical properties of the internal structures of these compact objects is completely missing. So we cannot really tell, in principle, it's not very easy to tell whether this compact object are black holes or not from the first principles. Of course, we have many other hints to tell us whether it's black hole or neutron star, but just from theoretical perspective, it's still very hard. Another aspect is, can we see some non-perturbative structures of general relativity? So with the LIGO Virgo data and this whole collaboration, one of the big project is to understand whether there is something beyond GR or whether GR is correct. So this what like motivates us to understand, to see whether there are some non-perturbative predictions we can make from general relativity, and to understand better of the structures of GR. So currently, I think most of the waveforms used in data analysis is like a close to merger for sure. It's non-perturbative. So what people do is do Padet resummation. And Padet is a very nice mathematical trick, but not many physics is contained there. So we need to also understand the physics behind these very cool resummations. Okay, so the plan of the talk will be the following. I will just first do a very brief recap about tidal effects, both basically tidal deformations and also tidal dissipations. Then I will start from black hole perturbation theory. I will start with Stokowski equations. I will tell you several ways of solving it. And then I will see that, okay, use this EFT and scaling amplitude techniques, we can extend the black hole perturbation series to really get a very interesting both physical and mathematical results, which is an exact anomalous dimension of multiple moments in GR. So basically, it tells you that the multiple moments defined in general relativity really depends on the scales. It has the typical RG roundings, which you already learned in your QFT course. Also, and later I will just tell you how we can practically use these new results to help us improve the gravitational wave waveforms. Okay, so let's start. The tidal effects is actually very simple. So this is probably the simplest effective field theory you have learned in your life. It's just the multiple expansions. So to write down the effective action is also very simple. It's just to couple your dynamic multipoles to external fields. So you can couple the electric quadrupole to the electric part of the gravitational field. You can also do the magnetic ones. And tidal effects, if you're thinking about our sun or some microscopic stars, and what is the the microscopic description of these quadrupoles. Basically, once you turn on some electric field, turn on some gravitational field, like what is the microscopic variables that will control the deformations? This is the called stellar fluid Lagrangian displacement. So you just have a fluid star. Then after you turn on the electric field, you ask yourself a question: is like, what is the fluid displacement? After you calculate the fluid displacement, you're able to calculate the quadrupoles the deformed quarter poles of the star. Also, like since we are in starting a linear response problem, once we turn on some electric field, we can ask a question like, what will the compact object respond? And the response function can be parameterized in this very nice form. So it's proportional to, first is some dimensional units. Lambda is the leading order tidal deformation parameter. It's called the tidal love number. And then you have this E is the electric field, and tau tidal is the tidal lagging time. So this tidal lagging time exists just because of causality. Once you turn on some external field, you need to give the compact object some time to respond. So this is just a very simple fact about causality. Then we can do the low frequency expansions, and at the leading order, you just turn tau tidal to be 0. It's an instantaneous response. And for this type of response, then you see that the love number will be proportional to the radius to the 5th power. And you can also extend to general multiples. The L is the multipolar index. For general multiples, it will be 2L plus 1. So this is very familiar on, like, I think from your E&M course. So as you can see, if for neutron stars, R will be big. So this is a huge number. Also, you can do the next leading order expansion. The next leading order expansion will be the parameter called H. H is known as the dissipation number. In astrophysics, I think people call it tidal heating. So we use this H here. And H is lambda times, basically proportional to lambda times T tidal over GM. You can use the fluid variables to write down the, to do some, order of magnitude estimates. You find that it's proportional radius to 6th power, which is even more enhanced. But it has another factor, which is this new or new BH, is new here, is the kinematic viscosity. So for kinematic viscosities, black hole puts your sort of bound, higher bound on this type of parameter. So basically, the kinematic viscosity is the mean free path times the average velocity. For black hole, the average velocity is like speed of light, so c is largest, and the mean free path is the size of this black hole, which is structural radius. So it sets the upper bound of this quantity. All of the other, let's see, if you calculate the fluid stars, our suns of some, and for typical neutron stars, it's very small, the kinematic viscosity. But if your neutron star has some extreme or equation of state, this number can be around 0.1. So for this type of neutron stars, dissipation is high, and we think probably in the future we will be able to see it if we are lucky. Also, feel free to interrupt me if you have any questions. Okay, so these are from mostly the EFT side, but are there any more interesting questions that we would like to understand, even from a theoretical perspective? So the interesting question in the EFT will be, we all know that point particles, if we call point particles to Einstein gravity, the theory is non-renormalizable. So we expect to see some UV divergences. And this gives us hints that there will be some new structures to happen. So we need to also study the renormalizations of these coupling constants or these correlation functions. So just a brief reminder of what is the RG running. So this is a very, I think famous example from QED. You just think about you have a propagation of electrons. So this P is the electron propagator in free theory. And in QED, the electrons is coupled to the photons. So once you calculate the self-energy or the two-point function, you need to also draw loop diagrams. And here you will see I draw this one loop diagram, which is the the self-energy contribution from the photon. And you calculate this diagram, you find, oh, it's diverging. So we need to add a counter term to cancel the superficial divergences, to cancel the 1 over epsilon. But the logarithmic term is physical. It tells you the RG running of the mass of the electrons. So I think similar things will happen also in this effective field, this point particle effective field series, which we use to study black holes and neutron stars. what type of things will happen is the following. You still consider similar, like some scattering experiments. You're shooting some waves towards the compact objects. So this wavy lines here is basically tells you the incoming waves. And the compact object oscillates, which basically it takes some time to respond. It oscillates and it emits wave again. But GR is highly nonlinear, which means that once the waves coming in or when the wave come out, the waves can get backscattered by the background potential. For example, here I draw this two-loop diagram, which is basically have two mass insertions. Two mass insertion correspond to 1 over r squared potential. So once the wave come in or wave come out, it gets backscattered with the 1 over r squared potential. And this diagram is UV diverging. So what is the meaning for that? It just means that you need to renormalize. You need to renormalize your quadrupole moments, your tidal response function of the compact object. Basically, the RG running of the measurements of the tidal response really depends on the energy scale where you do the experiments. So this is the RG equation, and we need to see calculate the pre-coefficient in order to study what will happen in the once we push the scale to the UV. Yeah, and to get more accurate predictions. Also, similar effects also happen in the places called gravitational radiations. So just imagine you just put the two black holes together. You're sitting very far away, and you treat the binary system as a single big single system. So you will also see similar diagrams here, and you just need to replace the mass of the compact object by the binding energy of that. If you draw similar loop diagrams, and similar divergences will happen. So, and the RG coefficient will roughly be the same. So it's very, very important to understand these RG runnings and these beta functions in order to help us to better, construct the waveforms, because these logarithms are typically very large. So we need to find these ways to resum it. Okay. So to answer these questions, and the way we approach the problem is by considering some spiritual scattering experiments. We call it gravitational Raman scattering. The scattering is not difficult to calculate. It's sort of very simple, because you can both solve it in the effective field theory side, and you can also solve it from the UV theory side. So by EFT here, what I mean is you couple the point particle, which is parameterized by the wall line, you couple it to the Einstein gravity. So in the effective action, I write down the wall line action, and also couples the Einstein-Hilbert term. Also at high orders, as we have seen, we need to describe the tidal deformations of the compact object, which is can be written by this Q dot E and Q dot B terms. Okay, so now you can draw Feynman diagrams. For Feynman diagrams, it's very simple to understand. So you have a source, which is this blob with the cross. It's the source. Then these dashed lines are offshore graviton, which basically is the potential modes. It's 1 over r is potential modes. Wavy lines are waves. So basically, just imagine you shoot some waves towards compact object. First, at the leading order, you get scattered by the Newtonian potential, which is 1 over r. And you can get recursive scatterings or sequential scatterings of the 1 over potential, which is the second diagram. You can get scattered with 1 over r squared potential, 1 over r to the cube potential, etc., etc. And at higher orders, you will see your scatterings also can hit the tidal operators. Basically, once you shoot the waves to compact objects, the objects oscillates, take time to respond, and emit a wave again. The real part will be the conservative tidal effects, tidal love numbers, dynamical tides, and things like that. And if you can use optical theorems, you will be able to see that it also allows you to calculate the absorption coefficient or absorption cross sections of the whole problem. And you can also solve these similar things in the UV theory, which is called black hole perturbation. So from in the past now infinity, you shooting some waves. Okay, crazy things happens in the middle. Some waves will enter in the black hole horizon. The other got reflected back to infinity. So this is the type of physical process we are going to solve. And we are currently actually on the way to study precision physics. And as you can see, so we have for the scalar toy models, for example, we are so if we do scalar wave scattering, so the incoming wave is not gravitational wave, it's scalar waves. For scalar wave scatterings, we are now able to calculate the rounding of the quarter poles and for general L at the second order. So G square is 2 p.m. corrections basically. And we can also to see that there's another rounding that comes from the post-Minkowskian corrections here. So basically, once you focus on the L equal to 0 is the monopole sector, you will see that there's a particular part of the RG rounding which is independent of the multiple on its own, but it's really the divergence of the divergence from the nonlinearities of GR. For example, here you are scattered with one of R cube potential. The diagram is diverging, so you need to add a contact term to renormalize the divergence. So this is basically the RG rounding of the dynamical love numbers for monopolar scalar scattering sectors. And we're on the way to precision physics is because we can use the standard particle physics tool. Let's see, we can do the DIMRAC, dimensional regularization. We confirm that the monopolar and the dipolar love numbers are 0 in this case. And in the MS bar scheme, we are also able to obtain the RG rounding and also the finite coefficients of the dynamical tidal love numbers. So this is the result. And now we are pushing this even further, also with some of my friends from the UCLA and the other places. They have already pushed this to 7 p.m. corrections, so 7 loop calculations, which is very, very, very impressive. Okay, so but from UV theory side, we can also understand this problem by looking at so-called Tarkovsky equation. So for Tarkovsky equations, it's a wave equation on curved background. And so I write this as a differential operator, curve, which is a wave operator, Laplacian on curved background. And this psi is a Tarkovsky variable. This is basically some contractions between your tetrads and also your physical field, let's say photons or gravitational field. And after you do linear perturbation theory on this background, you will find that the Tarkovsky equation is super nice because you can separate variable. After the separate variable, it becomes just the angular and the radial equations. And for the radial equation, like it's an ODE, so we need to study the singular structures of this ODE in order to solve the equation. The singularities is very nice because regular singularity at the inner and outer horizon and has irregular singularity at infinity. This irregularity just reveals the fact that there are some wave-like behavior. As you have learned in hydrogen atoms, once you solve the hydrogen atom, the radial equation, it also has an irregularity at infinity, which tells you it has like a wave-like oscillation behaviors. So the scattering experiment can be done in the following sense. We imagine at infinity, we have both ingoing and the incoming and outgoing waves. And with the proper classical boundary condition, we only allow ingoing waves at the horizon, at the outer horizon. So this sets up a proper scattering problem. And the whole process now becomes just to solve this radial wave equation with these boundary conditions. And it's very difficult because you are putting the boundary conditions at these two singular points. And mathematically, this is known as the confluent Hom function. So we need to write the linear combinations to linearly independent solutions at the infinity in terms of some regular solutions at the horizon. This is a very tough problem. It's also called the connection problem between these two singular points. Okay, so there are several methods to solve the equation. The first is a very traditional one called the MST method. The idea is to do the meshed asymptotic expansion. So near the horizon, you do a near zone expansion, which is in terms of some hypergeometric functions. And you can study the convergence radius of this functional expansion. You find that it converges at the outer horizon, but diverge at infinity. But the far zone solution, which is built upon series of clone wave function, which is very natural because like once you solve one of our potential, you're doing the solution is clone wave function. So you're doing this series expansion in terms of clone wave function. Then you find that converge at infinity but diverge at horizon. So how to make the series, this series valid at the whole regime is you need to do a matching in the intermediate regime, which we are like both series, both these functional series will converge. So this is a systematic way of like you're solving the ODEs near one singular point, some ODE near another singular point, you match them in their intermediate valid regime, then you get the whole solution. So this is the first way of solving the equation. And in this solution, in this way of solving the equation, there's a magic parameter which is mathematically known, but physically is mysterious. So this is called renormalized angular momentum. It was first proposed by MST in their remarkable paper back in 1996. This is the initial attempt to analytically solve the Gaussian equation. And this renormalized angular momentum was introduced, so-called the Floquet exponent or characteristic exponent of this equation. It tells you the asymptotic structure near the irregular singularity at infinity. But this has not been clearly understood. What is the physical and what's physical reason and what is the physical meaning of this parameter. But MST was very popular in the gravitational wave community. So like it has been widely used in cell force calculation, waveform modeling, and a lot of the calibrations and the waveform construction all based on these methods. So, but unfortunately, for 30 years, people don't have any clear physical understanding of this parameter. And then a very recent progress of studying Tarkovsky equations come from the conformal field theory community. And there's a very famous formula called Trieste formula. So these methods makes use of something very, very fancy. It's called the BPZ equation. So you have insert 5 prime operators, and there's a 1 degenerate field. It's level 2-1 insertion. And this for sure, its correlation function satisfies the BPZ equation with this type of potentials. And this potential takes this following form. So now this looks very abstract, but you can take the classical limit. After you take the classical limit, you will see that we all know, like from the famous, like argument from Zabolochikov, we're saying that the conformal block will exponentiate. So you can write as a, overall amplitude times exponential of some classical, so-called classical conformal block, which you can have many ways to systematically calculate this conformal block. And magically, this pre-coefficient psi satisfies the Hom function, which is exactly the form of the Tarkovsky equation. And by using the, the properties of classical conformal block and the fusion rules of the CFT correlation functions, you will be able to obtain the following very compact expression, analytic expression. So I will not write all of these things in detail because that's very complicated, but I will just tell you the final results. The final results is that so you have C, which is called connection coefficient, is exactly the same that we want to solve, also it's exactly the same that we enter in the scattering amplitude. There is a fusion term, which is the ratio of these gamma functions, if you're familiar with conformal field theory. And there's another systematic correction come from these ratios of the classical conformal block. So it's a very classical, it's a very systematic way of solving the equation. And with this method, it's a mathematical tool, you can map the Tarkovsky equation to this home functions, which is written in terms of CFT parameters. The mapping is done with this following way. So in this slide, I basically show you the the actual factorized formula using black hole parameters. It factorized into the called near zone and far zone pieces. The near zone piece is, as I have said, it's converge at horizon, diverge at infinity. Far zone, it converge at infinity but diverge at the horizon. And you see, like all of this compact is a very compact form. So as f is something called this Nekrasov flexibility function, which allows you to do perturbative expansion in terms of this instanton parameter, but it's instanton. It's okay, so it's some fancy parameters, but you can just think it as a post-Minkowski expansion. So epsilon is the post-Minkowski counting, and you can see in the later dictionaries, epsilon is proportional to L. So instanton expansion is the same as post-Minkowski expansion. And this A has a fancy name called quantum A period. It basically tells you the period once you are traveling around the classically allowed regime in a potential scattering problem. And magically, it relates to this renormalized angular momentum. So there are some, like formal understanding of that. And this characteristic exponents also appears in conformal field series. Also, we have this tidal response function k, which appears in the near zone part, and this k is basically captures the tidal deformabilities of the compact objects. It can be black holes or can be neutron stars. So all of this mass is M1, M2, M3 is we are using this supersymmetric gauge theory analog or the dictionary of the CFT is called AGT correspondence. So, but anyway, so it's just we can use all of these dictionaries to map the black hole parameters and either the spin, extremality, PM counting parameters to all of these CFT parameters and also in the gauge series. Okay, so it's a compact exact formula, which it's very nice. Also, like we can also do a detailed study of the far zone and the near zone physics. So in terms of far zone, basically what we were doing is we were doing the expansion of in the like in power of G. The weak field expansion is what we are interested in. The far zone describes black holes in spinning point particle limit, which is very natural because in the far away, it's just a point particle with some spins. And far zone phase shift is elastic. This is also intuitive because there's no horizon, it's not there, so there's no absorption. And the phase shift is polynomial in terms of black hole spin. This is very interesting. It's an mathematical facts. Also, it aligns with this EFT philosophy because once you want to describe spinning particles in the EFT, you can do you need to do Taylor expansion in terms of spins. So it's analyticity in terms of black hole spin, which is aligned with spin-induced multipolar expansion. And this very fancy function is f, it's called the Nekrasov flexibility function. You can compare with more traditional methods. You find that in traditional methods, you are doing like infinite sum of power series in terms of G, and nicely somehow it resumes to a function in CFT. So there are some hidden conformal structures. Currently we still have no clear clue of what happened. So if you guys have any interesting ideas of those, how to proceed on this problem, it will be very cool. Okay, so for near-zone physics, it's also very interesting because we can also get the exact formulas. So here, this K is the exact tidal response of the black holes. It looks very complicated, But the first part of these gamma functions you can reproduce with the traditional dictionary of ADS-CFT. And so here we also include the high order corrections. And as you can see from this formula, it's non-analytic in G because it's A, this a renormalized angular momentum of quantum periods is typically not integer, so it's non-analytic in G. This means that no matter how many Feynman diagrams you calculate, you draw Feynman diagrams, you cannot really probe any near-zone physics. That's impossible because it's intrinsically non-analytic. Also, the near zone has absorptions because black hole has a horizon. And you can also modify that to neutron stars if your fluid star has a viscosity. And we can also get the exact quantization condition of the quasi-normal modes, which is the pole of the scattering amplitude. So it's an exact algebraic equation, which you can solve for quasi-normal modes. Okay, so at this stage, we have a much better understanding of what is renormalized angular momentum with the properties coming from conformal field series. And these properties allows us to calculate and also to establish a universal scaling relation, which is at high frequency, nu scales with -2i gm omega. It's very, no matter for the spin of the perturbations, the spin of the black holes, no matter for the angular like multiple index, this is universal. So it's a very interesting observation, and the progress we can make from conformal field theory perspective. But the physical meaning is still unclear. So you still need to seek for the physical understanding of what is new. But with these CFT methods, we can go beyond the 4D case. So this is a recent, also a very recent result that we get for the 5D black hole scatterings. Okay. So, but what is really the physical understanding of the renormalized angular momentum? So I come up with this idea just one night before, one night before I go to bed. And I finally realized that we can just do simple dimensional analysis. We know that for the tidal love numbers in Newtonian gravity is proportional to radius to 2L plus 1. And which corresponds, if you do scattering experiments like in Newtonian gravity, for example, you're shooting some waves towards our sun, you will get a phase shift which is R omega to 12 plus 1. This is the typical phase shift. But in GR, as I was saying, like this, you just need to replace the typical angular momentum with something so-called renormalized angular momentum. This is from the exact formula. You can see that. It's just this very, very simple replacement. And so which gives me an idea that maybe I can play with these formulas. So I just come up with a very simple algebraic trick, which you rewrite the GR phase shift, factor out the Newtonian piece, and just reparameterize the left part. So this is a very simple algebraic trick. With this trick, now you see something familiar. You can take the logarithmic derivative of the scale mu. The scale mu is the artificial scale, which is like in QFT we call the matching scale. I introduced by hand, and for sure the final physical answer will not depend on mu. But if I introduce mu by hand, I can treat the coupling constant, let's see, which is r times mu part, which is sort of the scales of the compact object. I can take the logarithmic derivative. And then you see some very nice nice form, which is analog of the RG equation of the multiple moments, right? You see something similar to the RG equation. So now at this point, we sort of have an intuition that this renormalized angular momentum is a good name. It's not only just a fancy name or like mathematical facts that we need to solve the equation. It also is truly related to the renormalization of multiple moments in GR. So how to establish this more concretely is we need to really perform the loop calculations. For example, you draw Feynman diagrams. It's a two-loop diagram, and you can calculate the loop corrections. So this is a proposed formula. which is this RG equation for the 2-point function, which is the tidal response function. And then the two loops, I think many people have calculated the beta function coefficient. And the beta function coefficient, which is a two-loop order, it's have this number, and it has been confirmed by many papers. And recently, as you can see, it takes almost like 14 years for people to get the 4 p.m., which is 4 loop corrections. Very impressive, very hard to calculate. And then, so with my proposed formula, we check the 2 loop and 4 loop all agree. And for me, because we have this mathematical ways to solve the Tarkovsky equation, we have this very fancy methods, so we can get this renormalized angular momentum to very, very high order just by press the button. So here is a new prediction. Let's say the 6 loop order. If someone is, it maybe takes 10 more years to calculate 6 loops, but so we now can just provide you the numbers. Also, we can solve this for the generic multiple moments. You can do like octuple and even high order multiples just within a minute. So with this formula, this key interesting observation, we can skip all of these loop calculations and provide a universal formula for that. So it's an answer to a 30-year-old question, which is that this renormalized angular momentum, mathematically known as the flow kit exponent, can be understood as the anomalous dimension of tidal operators, which accounts for this thing called tail effects, which is the back reactions from the potential. So what kind of implications we can use this to this running of the tidal operators to understand, also to make predictions for the actual gravitational wave, which is come from the multipolar radiations. So you can see like from the previous diagram, if you just compare, you sort of just cut the diagram by half. So for this, take the first 2 diagrams, cut it by half. You will see it's just this the same diagram will appear also in radiative components. So for the effective field theory, if you for a binary system, then you can see that you just need to replace the mass of the single object with the binary of the binary, the spin of the single object with the angular momentum of the binary, and all the others are the same. So you also have the similar RG running properties, which is the RG running of the multiple of the radiative multiples. So the leading order will be the famous Einstein quadrupole formula. But now we kind of like attach the corrections from the background potential, which come from the corrections from binding energy. So here, as you can already see, with this very simple formula, we can predict all of these PM corrections just once and for all. So instead of really doing loops, now just press the button and you get the answer. So also you can write down the solution to the RG equation, which tells you the running of the multiples in GR. Also, if we want to be more formal, and here is a formula which for generally compact objects, if you are powerful enough to calculate the scatterings against a binary, then you can get the anomalous dimension for the radiative multiples by doing some linear analytic continuation of the phase shift from positive frequency to negative frequency, sum them together, and you get the final answer. And we have already confirmed this by many examples. Okay, so with this nice formula, let's see practically what kind of things we can do. Practically, whether we can really improve the waveform analysis or the waveform model building. So as has been pointed out by Damore, which was saying that the gravitational waves you really observe can be effectively written in this factorized formula. So you have some conserved EOB energy, which is captures the conservative dynamics of the binary system, and you also have the tail resummation, which is in principle come from the nonlinear wave propagation on the nonlinear background. So, and there will be some phase correction, amplitude correction come from post-Minkowski and post-Newtonian corrections. So historically, people has figured out leading theory summation, also by Damois and Nagar. So the leading theory summation can be written in this very nice form. S is known as the Sommerfeld enhancement factor. It basically tells you that once you have the potential, which is one of our long-range potential, you can enhance the scattering cross sections by this type of amount. So this has been widely used even in your study of hydrogen atoms. You can calculate the wave function ratio with and without the 1 over potential, which tells you the enhance of finding the 1 over potential, the enhancement of the probability of finding the particle. Basically, and it also has been used in the dark matter detection with the Sommerfeld enhancement. So here is a gravitational analog of that process, whereas you have 1 over potential, which is true in Newtonian gravity. And also, because of this long-range IR divergences, so as has been pointed by Weinberg, the like scatterings in a long-range potential has IR divergences. So that's where you see this logarithmic term in the phase. But now we have a much better prediction, like an improvement of these resummations. So S is the improved Sommerfeld enhancement factor. It's basically from the simple observation that if you replace the multiple index L by nu, which is nu is something universal, and it also appears in the RG running, so it's something which is independent of the properties of the compact object. You can get this Sommerfeld enhancement factor. And you can also get the improved phase shift just by adding the corrections from the nu, and also there will be some the corrections from the solution to the RG equation. So these are the universal pieces we can get from renormalized angular momentum from the solutions to the Tarkovsky equation. So just magically, like you see, the solution to the Tarkovsky equation has a nice mathematical property of this renormalized angular momentum, and with the effective field theory techniques, we can use this quantity and to really input the waveforms. So you go from a single body scattering, and you now like you find some universal property, then you can apply it to a real world binary problem. Let's see how well with this this formula. So basically, let's see how does it perform. It like it is really improve the waveform or no? So if you just naively look at this beyond the probe limit, there are so many these transcendental numbers, it's pi's, log, and Euler gamma functions. But with our proposed resummation, the funny thing is that all of these transcendental parts are almost gone. Well, there's still one part which is at 4 p.m. still one function left because that comes from the tail of memory. For the tail of memory, our proposed RG cannot resum that, so it's still beyond our scope. But all of the previous terms we have resummed it, so it gives us hints like this formula really does a good job. So let me quickly summarize. So in this talk, I basically tells you like wall-line EFT is very useful. It gives you a model-independent way to study tidal effects of compact binaries. And we use gravitational Raman scattering, even though it's a spiritual scattering experiments, but we can get, it's a very nice gauging event way to study compact objects. And the analytical tools, and we have the very cool use of the Tarkovsky equation from various mathematical or even traditional techniques. We find that it can give us an exact anomalous dimension of GR multiples. Especially this renormalized angular momentum, it provides us with an efficient way to perform the resummation. And our initial result shows that it really does a good job. Okay, thank you. Yeah.
Thank you.
Any questions?
Yes, we can pass to the question session. So here we have a lot of students. So please, if someone have questions, come close to the computer in order to do your questions.
Sorry, I cannot hear you.
We are reading questions, guys. Okay. Also online, someone that has questions. Okay, come. If you want to.
Hello again, Zihan. It's Jacobo again. So in your in the slide number 13, I think, where you start to talk about the Tulkowski equation for the wave functions, is that the part that you where you sort of retake the amplitude program and you put everything in a like an S matrix, or where is the part where you can like somewhat explicitly see see like amplitudes, as in like waveforms, for example, in the K-Mach formalism and these things?
Can you repeat again?
Yeah, is that the like the how do you put the Tulkowski equation in as an S matrix, or where is the part where you start?
Okay. Yeah. So it comes from here. It comes from. So basically, like, so we are doing a wave scattering problem against let's see, a compact object. So you can do in the EFT way, which you just write down the action, get Feynman rules, or like things. You can just calculate the scattering amplitude as a traditional way. For sure, you can use like either operator based formalism like K-Mach, or you like just use textbook way. So there's no difference on that. And the saying is that because essentially from effective field theory side, you're also you are solving a wave scattering problem against a binary. The only difference is that the binary in EFT is modeled as a point particle with multipolar moments. But in the UV theory, you also have a scattering experiments. You are shooting waves from past infinity, and you calculate what comes outside, what comes to the future non-infinity. So the scatterings in the EFT is the same, will be the same as the solutions of the scatterings, a scattering phase shift you calculate from the Gauss equation. So similar things, I think you may learn that also in your quantum mechanical course, is like you can calculate the scatterings against hydrogen atoms by traditional techniques like Feynman diagrams. Also, you can calculate the scatterings of the hydrogen atoms by solving the radial shooting equation of the hydrogen atoms. You can extract the scattering phase shift by doing partial waves, or you can even study the scatterings of the bound states, right?
Okay, yeah, thank you.
Yeah, so which is just an analog of what you have learned in quantum mechanics.
Yeah, okay, that makes sense. Thank you.
Okay, thank you, Jacobo. More questions, guys? No? Online? Come on, there's no naive questions.
Well, any question is okay, yeah.
Okay.
Any question is okay.
Well, we thank again to Zihan, and we hope that we could have in another time for another amazing talk. Thank you so much.
Thank you. So let me stop. Okay. All right. See you.
Thank you.
Bye.